Hi everyone, and welcome to Pre-Algebra 7, BCPS-TV style. I'm Mr. Parker, and I'll be your host as we work through today's lesson, which is all about how we use probability. Why study probability? Chance and randomness are some other names for probability, and they affect many aspects of our lives, from predicting the weather, to winning at your favorite card or board game, to setting insurance rates. Today's lesson will cover these objectives, which are the same as week 4 of the Pre-Algebra 7 BCPS Remote Learning Packet, which is the week of April 27th. Students will learn how to describe the likelihood of a simple event, find the probability of an event and its complement, find experimental probability and use the information to make predictions, find theoretical probability of simple and compound events, and use theoretical probability to make predictions. It sounds like a lot, but you'll be okay. Here's a Desmos activity called Chance Experiments. We're going to use this to highlight some ideas about probability. So this is inviting us to play a game, and here's how it works. We're going to spin the spinner, and how do you win? That's up to you. Two options. We can either choose to win when we land on red, or win when we land on blue. Which one would you choose? Personally, I'm going to choose win on red. And the reason that I'm choosing the win on red is the area of the red section of the circle is bigger than the area of the blue. Awesome. Well, now we get a chance to play. I chose win on red. I'm going to press spin to play a practice round. Yes, I won! You originally chose win on red, and you won the practice round. If you were to play the game many times, say 36 times in a row, which option would you choose? I think I would stick with win on red. Now, it's asking me to explain why I would pick stay with red, or win on red rather. And what I'm thinking is, well, if we played 36 times, I wouldn't expect to win every time, but I would expect to win a lot of times. And that's our goal today, is to figure out about how many times I would think that I would win if I chose win on red. Let's review some vocabulary. Probability is a number from 0 to 1 that describes how likely an event is to occur. Looking at our spinner example, the theoretical probability of landing on blue after one spin is 1 out of 4, and the theoretical probability of landing on red is 3 out of 4. This is because there are 4 equal sections, even though only 2 unequal sections are drawn, and 3 of those 4 equal sections are red. I'm going to draw in a line to show where those 4 equal sections would be. And now we can see that 3 of those 4 are red, and 1 of those 4 is blue. We can also write this probability as 3 over 4, or 75 hundredths, or 75%. That's the chance we will land on the red section of the spinner. For the blue section of the spinner, the chance would be 1 out of 4, or 25 hundredths, or 25%. We can write probabilities as fractions, decimals, or percents. The reason this is called the theoretical probability is because the theory is that the spinner will land on blue about 25% of the time and on red 75% of the time if we were to spin the spinner a whole boatload of times. Today's lesson has lots of vocabulary, which should be on Schoology or in your print packet, so don't try and copy all these definitions down now. I'll be using the vocabulary as we go through the problem, so you may pick up on some of the meanings just by watching and following along. An experiment is an activity involving chance in which the results are observed. In our spinner example, spinning the spinner once, twice, or 36 times was the experiment. An outcome is the possible result of a probability experiment. In our spinner example, there are 2 outcomes, landing on red or landing on blue. The sample space represents all possible outcomes. In this case, landing on red or blue would represent the sample space. Landing on green is not a possible outcome, so it is not in the sample space. We have one more vocabulary term, which is the complement of an event. That is all of the outcomes in a sample space that are not in the event. So the complement of spinning blue, in this case, would be spinning red, because that is the only other thing that can happen besides spinning blue. Let's continue with our Desmos activity. This time, I did choose win on red, and where we left off last time, we were going to play 36 times and see what happens. Well, did you make a guess? How many times do you think I will win if I play this game 36 times if I chose win on red? We did look at the probability and said that it was about 3/4, so I would expect to win about 3/4 of the time. And 3/4 of 36 times would be 27 times. So let's spin these 36 spinners and see what happens. Oh, pretty close. I landed on red 25 times out of 36, which is just under 75%, and 11 out of 36, which is just over 25%. So pretty good, pretty accurate there. It was about 31% on blue. Here shows the entire class's results. 1,265 spins landed on red, 427 landed on blue out of a total of 1,692. I would say that it appears more likely for us to land on red, and it does look pretty close to our theoretical probability of 3 out of 4 times. Here we have a probability scale. This is something that helps us rank the likelihood of an event. How likely is each event? Well, we're going to move the points along the probability scale to indicate our answer. Landing on red was not equally likely as landing on blue. It was definitely more likely, but it wasn't quite certain because it didn't happen every time. For blue, it wasn't impossible to land on blue, and it wasn't equally likely. It was a little bit less than equally likely, so I'm going to put my dot right about there. Defining the probability of an event, we take the number of outcomes in the event and divide it by the outcomes in the sample space. Because an event is always smaller or the same size as the sample space, this fraction will always be less than or equal to 1 or 100%. For example, the probability of rolling a number greater than 2 on a number cube is 4 out of 6 because there are 4 numbers on the number cube that are greater than 2 out of the sample space, which is any number that it can land on. So the possibilities are 3, 4, 5, or 6. Now, of all the possibilities on the number cube, we have 1, 2, 3, 4, 5, 6, which means that our probability will be 4 out of 6, which can be simplified to the fraction 2/3, or written as a percent, and it is approximately 67%. The complement of rolling a number greater than 2 is rolling a number that is 2 or less. What would be the probability for that? How is that related to 67%? If you said that the answer is 2 out of 6, or 1/3, or 33%, you're correct. The complement of an event will always be 100% minus the probability of the event itself. In other words, the probability of an event plus the probability of its complement should be equal to 1. Now you try. This spinner has 8 equally sized sections numbered 1 through 8. What is the probability of each event? Our first event is spinning to land on a prime number. So the first thing that we're going to need to do is figure out which numbers are prime. So the prime numbers here are 2, 3, 5, and 7. 1 is not a prime number because it does not have exactly 2 factors. So what is the probability of spinning and landing on a prime number? Well, there were 4 spaces that had a prime number out of 8 total spaces. So the probability is 4 out of 8, or 1/2, or 50%, or 5/10, or 50/100, however you would like to phrase that. Let's try another. This time, what is the probability that you spin and land on a number that is less than 3? If you chose 2/8, or 1/4, or 25%, or 25/100, you're correct. The numbers on this spinner less than 3 are 1 and 2, and those are the only options. Question C asks us, what's the probability that you spin and land on a 9? If you're a little confused, it's understandable. There's no 9 on the spinner. So what's the probability that you land on a 9? 0. None of the spaces have a 9 on them. So the probability in this case is 0 out of 100. 0 out of 8, which is equivalent to 0 out of 100, which is equal to 0%. There's lots of different ways that you could write 0, but this is an event that is impossible. It is impossible to spin this spinner and land on a 9 because there is no 9 on this spinner. So this is a case where we have an event that is truly impossible. We have one more. What about spinning and landing on a multiple of 2? Well, which numbers will work? Let's circle them. 2, 4, 6, 8. Who do we appreciate? Mr. Parker, Mr. Parker. Yeah! Sorry, got a little carried away there. But that is 4 numbers out of the 8 that are on there. So again, we are at 50%. Oh, last one. I said the last one was the last one. I forgot there was a 5th problem on here. What's the chance that you land on a number greater than 3? If you answered 5/8 or 62.5%, you are correct. The last examples that we looked at were theoretical probabilities because they were based on ideas or theories. We didn't actually spin the spinner that had 8 equal spaces. We did spin the red and blue spinner 36 times, so we have both a theory and an experiment to go with that. And so what we're going to dive into is the difference between the theoretical and experimental probabilities. Experimental probabilities are what we see when we actually perform some type of experiment, like when we did the 36 spinners of the red and blue in the Desmos activity. These probabilities are related, but slightly different. Here, we're given the results and asked which spinner might have been used. Malik and Mia played 36 rounds with a different spinner, and the results are shown in the table. Which spinner did they most likely use? Well, I see that they landed on red 17 times and landed on blue 19 times out of the 36 spins. That's pretty close to 50-50, so I would expect the blue and red areas to be about the same. Looking at this seems like it's way more likely to land on blue than red, and even though I landed more on blue than red, it wasn't a whole lot more, so I'm thinking that this probably is not the right answer. Here, the red and blue sections are about equal, but there's also this black section of the circle, and I don't see a land on black in the table, so I would expect to see some landing on black if there were 3 possibilities, but I only see 2, so it's probably not that one either. Here we have a circle that has 4 equal sections. 2 of those sections are red, or 1/2 of them, and 2 of those sections are blue, also 1/2. This one looks like it could be a good candidate. And similarly, this spinner has half red, half blue, pretty close to our experimental probabilities. So our experimental probabilities were 17 out of 36, which is slightly under 50%, about 47%, and 19 out of 36, which is slightly over 50% at about 53%. So pretty close to the theoretical, or what I would expect just based looking at the spinner. Now here we are asked to drag the movable point to create a spinner where landing on red is almost impossible and blue is almost certain. So I'm going to move my dial here. Oh, that's pretty close. That'd be really tough to get a red. Not quite impossible, but pretty close to impossible. Let's see what this does for us. We're going to play 36 more times. How many times would you expect to land on a red? There is a sector there, but it's small. Let's see what the results are. Oh, I got 1 red. Oh, looks like 1 out of 36. So about 3% of the time. That seems to go with our theoretical probability that it would be really difficult to land on red and that most of our spins should land on blue. A compound event is an event made up of 2 or more simple events. A common example of this is rolling 2 dice, which is compound because rolling each die is a simple event, so put together it is a compound event. What is the probability of rolling 2 dice and getting a sum of 8? How many total outcomes are possible? It might help to have a little demonstration.
Let's look at the sample space for rolling 2 dice. Here I have a white die on the left and a blue die on the right. One possible event would be rolling a 1 on the white and a 1 on the blue for a sum of 2. I could roll a 1 on the white and a 2 on the blue for a sum of 3. I could roll a 1 on the white and a 3 on the blue for a sum of 4. There are lots of possible events here. Can you figure out exactly how many there are?
Here's a visual of the sample space that shows all 36 possible outcomes. Of those, 5 have a sum of 8, so the probability of rolling a sum of 8 with 2 dice is 5 out of 36, or roughly 14%. What sum or sums have the highest probability of being rolled? If you said 7, you are absolutely correct. There are more 7s on this sample space diagram than any other number. The chance of rolling a 7 is a 1 out of 6 chance, or about a 17% chance of being rolled. What about the lowest probability? There are 2 answers here, 2 or 12. Each number only appears once in this sample space. So there is a 1 in 36 chance of rolling a 2 and a 1 in 36 chance of rolling a 12. They each have a probability of roughly 3%. Here's another compound event problem. A deli prepares sandwiches with bread, white or wheat, meat, ham, turkey or chicken, and cheese, cheddar or Swiss. Each combination is equally likely. Find the probability of choosing a sandwich at random and getting turkey and Swiss on wheat bread. There are 3 simple events: picking a bread, picking a meat, and picking a cheese. Together, they make a compound event. Before we answer this question, we're going to try and use a little visualization. A tree diagram can be a useful visual here. Turkey and Swiss on wheat is represented by this outcome. Here is wheat, turkey, and then Swiss. So we are following that path. There are 12 total outcomes represented by this column all the way on the right. So the probability of getting a turkey and Swiss on wheat is 1 out of 12, or about 8%. Thank you for joining Pre-Algebra this week. Here's a photo of my wife making gnocchi. We had to do lots of measuring and volume work to make a 9-inch by 5-inch loaf. Then eventually we needed to cut it into 1-inch bites. It was tasty. See you next week. Stay safe and wash your hands.